So we're thinking about the steps to solve exact equations. And they get a little bit long. So our first requirement is that we need to make sure we have our ODE in the form of an exact equation. So we're going to need some m that can depend on x and y, but doesn't necessarily have to be both like we saw in the previous example, times dx plus n, again a function of either variable, times dy equal to 0. And just like with separable equations, if it's not in that form, you can rearrange it. But we do need to check that it is exact by that partial derivative condition, that partials of m with respect to y and partials of n with respect to x need to be equal. I'm gonna go ahead and add right here a little like sub-step 2b. This is gonna be about how we deal with problems where that's not true. And I want you to leave a gap in your notes so that you can fill that in later as well. But we're just gonna first assume everything in the process goes right, and then later we'll fill in this step about how we deal with when it goes wrong. So for now, we'll just pretend that's always gonna happen. And then if we have an exact equation, we're gonna integrate m with respect to x. And we're trying to find some f of xy that we think we find by integrating m with respect to x. But m carries information about x. We might be missing some information about y afterwards. You can think about that g of y as being the constant of integration for an integral in only the x variable. Then we're going to note that if we take this equation and solve for g, we would get that g is f minus the integral of m dx. We already calculated integral of m dx. And the derivative of g with respect to y is going to be n minus dy of that integral of m with respect to x, where m is carrying information about derivatives with respect to y. That's why we put it in when we look at taking a derivative of f with respect to y. And we just need to compute that. Then we're going to integrate to find g of y equal to the integral of everything we just wrote down. And that looks very messy, but in practice, this quantity right here is going to be something that you compute. It's going to be like e to 3x, and then you're going to integrate it. It's going to become e to 3x times y. So it looks gross in general terms, but in practice it gets a bit easier. And then we're going to go ahead and plug that thing we just evaluated into this third step right here where we had g that we didn't know. In the previous step we found g, so we just plug it in. And we will go ahead and get that f of xy is that first integral we took plus that second integral that we just took. And then we're going to set that function f equal to c for some unknown constant. That's how we introduce the unknown constant that our general solutions need so that we can solve many different initial value problems for a given equation. And then if you can, isolate y so that you have an explicit solution to your differential equation. That's not always going to work out. These solutions can get a little bit messy. Just, try it and then leave it in the nicest looking form you can, if not.